Swayam Prabha. Digital India. Educated India.
So in this lecture, we will continue our discussion on estimation of errors in MD simulations. So in the last lecture, we looked at a few methods by which we can measure errors in the quantities in MD simulations. One approach is to get time correlation function, and from there get the autocorrelation time, and then from there we correct the data to estimate the error. The other way is to do a blocking operation, whereby we make the entire data set into several groups, and then from there we can find out what is the statistical inefficiency. In other words, indirectly, what is the correlation length of the data. So those two methods we have looked at in last lecture. So we will continue along the same line. In this particular lecture, I would like to discuss a very simple method known as block average method, which resembles the blocking operation we did in the last lecture as well. So this is actually proposed by two scientists, Flagship and Peterson, and this method is very simple to implement. For instance, let's say you want to look at the error estimate of certain property A in MD simulations, and we record or store the value of property A at different time intervals. Let's denote them as A1, A2, and then you might have some AL, number of property A stored. So once we have this data stored as a function of time, A1, A2 all the way up to AL, where L is the number of samples, and we can do what is called the ensemble average or the run average or the time average by summing over this property AI over the entire sample. So we have seen something similar in the last lecture as well. And then if all this quantity AI are statistically independent, then we can find the variance in the mean by sigma square A by the, so this tau run is nothing but L here. That is the total number of points in this particular set, where the definition of sigma square A comes from the formula given here. That is, we look at AI minus the average, square them, and then sum over all the sample L. But we know that not all this data points in this L will be statistically independent. So there will be some correlation among the data set itself. So in this block average method, we conduct certain operations by which we try to eliminate this correlation. So the way this method works is, again you take this entire data set, L number of data points, and then we group them into consecutive blocks, and then we calculate the average for each block, and then these averages, as you continue this blocking operation, we will see that these block averages will show lesser and lesser statistical correlation, and then if the block size is made sufficiently large, we can see that all these data sets would be uncorrelated. And when we are sure that there is no further correlation, then we can use the standard formula, which is this, to get the error calculation, provided that we know what is the block size. So let us illustrate this particular method, by which we say that initially we have the data set A1, A2, A3 all the way up to AL. Okay, this is a raw data set we would have stored in MD simulations. Now we want to transform this set of data into another new set of data by a simple blocking operation. For instance, we want to create a new data set A1 prime, A2 prime all the way up to A prime, L prime, where each data set AI prime is basically the arithmetic average of two consecutive data sets. In other words, A1 prime will be half of A1 plus A2. Similarly, A2 prime will be half of A3 and A4, and like that. So what we are trying to do is, in the first blocking operation, we take two consecutive data set 1 and 2, 2 and 3, 4 and 5, etc. and then we average those values and create a new data set. By doing this, the total length of the data set would have become half now, because we have grouped two sets into one data. So this is one blocking operation, and then once we have this new set of data, we will see that the mean value of A remains the same whether we have done the original data set or the newly transformed data set. They are going to be the same in terms of mean. However, if you calculate the variance, you see that the variance becomes different because of this local averaging. So with this new data set A1 prime, A2 prime, A3 prime, etc., we apply the formula to calculate the variance for the new data set. And in this new data set, we will calculate this, and then in the next block operation, what we will do is, we take this new data set A1 prime, A2 prime, and then make another new data set which is called AI double prime using the data set of A prime. In other words, A1 double prime would be half of A1 prime A2 prime, and similarly A2 double prime would be half of A3 prime A4 prime. So, by this we would have reduced the length of the data set by half of L prime, or 1/4 of the original data set L. So, at every block operation, what we are trying to do is we are compressing the data into half, and we continue this operation. And then as we continue this block operation, and each of those blocks we calculate the variance, and then we can plot the variance or the square of the variance versus the block operation. And then we will see that once this data becomes uncorrelated, the data set, we will see that the quantity sigma square by L prime will become constant. And to see that, if you look at this particular circles, we start with some 600,000 data set to start with, and we make this 600,000 data sets into 300 data set, and from 300,000 to 150,000, etc., etc. And then we continue to do this. Each of those corresponds to this blocking operation. So, when m equal to 0, that means we are operating the entire data set of 600,000. When m becomes 1, we mean that this 600,000 data set is now reduced into 300,000 data set. That means we have halved them. And then we make estimate of the variance from this formula. And then we continue this. As you can see, as we increase this blocking operation, you see this standard deviation or error here attains a plateau value about here, where no longer it depends on the blocking operations. So, this plateau value is what we would like to look at, and we consider this is the true error value, and then we take that as a error estimate, and then take a square root of sigma square by L, and that is going to be the error in the measurement of average A. You can see that after the plateau is reached, you see some noise coming up as you continue this, because as you go to larger and larger blocking operation, you get lesser and lesser data set. Okay, and this is more amplified if you look at this data set, where initially we had only 150,000 data sets. So, when you do blocking operation, you can see that the plateau has not really reached properly, because the amount of data set to start with itself wasn't enough, and because of that you can see that there is a large error coming up to start with. So, what I am trying to say here is that in MD simulations, we have the choice of how many data points to store. If you have stored sufficiently large number of data sets, then we can subject this data set for this blocking operation, and then we hope to see this kind of a plateau value on the error, which basically indicates that around this region the data sets are statistically uncorrelated, and then we can take this estimate of sigma as the error estimate. You might, when you see this kind of a behavior where the plateau is not clearly established, this is an indication that the amount of data set to start with is not good enough, or it's not enough. So, we have to store more data set, and then we have to ignore the noise that is coming up in the larger number of blocking operation, because the number of data sets here would be reduced much lesser. You might have just few points, maybe 2 or 4 or 8, etc. So, this method is very simple to code, and it's very easy to do as a post processing step. And once we have this sigma estimated, then we can give what is the confidence interval, what is the error estimate for the measurement. Now, when we report simulation measurements, we sometimes write the property of A is equal to some mean plus or minus sigma. So, this sigma here is the error estimate which you would have got from the gotten from the block method or block average method. Now, in your simulation, if you just simply say that the value of property A is just an average, what we mean by that is as if this particular property behaves like a delta function, that means it has a one unique value. But then we know that from thermodynamics that the properties are distributed as a Gaussian random variable. So, this picture is not entirely true. So, we have to give a error estimate or the variability in the measurement of A. So, for that we generally give the value of A not as simply average, but plus or minus some sigma, which is a standard deviation or error estimate here. So, when we think about this property A as a Gaussian random variable, and then when we write A as mean plus or minus sigma, what we mean by that is we say that the value of A given by this average value is within the 68% of the confidence interval. So, that means if I take 100 samples, it is likely that the 68 of those 100 sample would have the value of A given by this mean value. And then if you want to increase this confidence interval, we can increase this error estimate. We can give 2 times sigma or 2.5 times sigma. And then you can see that by we increase the confidence interval of the measurement. So when I say the property A is given as the mean plus or minus 2 sigma, I can say that the value of A given by this average is within 95% confidence interval. And then when you give 2.6 sigma, we can be saying that the value of A is within 99% of the confidence interval. All this confidence interval is basically obtained from a Gaussian distribution about the mean. So as you can see, the mean is somewhere here, and then when you take plus or minus sigma, the area under this curve basically tells the what's the probability that this value will be within this bound, and that becomes about 68%. Similarly, when you increase this interval to 2.6, which is somewhere here, so if I report this value of A in this particular interval, then I am pretty much sure that 99% of the time the value is actually within this particular interval. So when you there are two steps involved. First, we measure the averages, and average doesn't depend on all the blocking operation, various operation we have done. So average is a time average or an ensemble average, and after that we get an error estimate, which is a statistical error estimate, and that estimate comes from various methods. And then once you have sigma from those measurements, then you have the choice of representing mean plus or minus sigma, or mean plus or minus 2 sigma, or mean plus or minus 2.5 sigma. Each of those means that you are giving a certain confidence interval for these measurements. So typically you see the measurements being reported as mean plus or minus sigma, and we have to remember that the implication of that result is that the value of A is within 68 or close to 70% confidence interval. If you want to increase this confidence interval, then we have to give the values in terms of mean plus or minus 2.5 sigma. So far all our discussion was looking at error estimate in equilibrium averages, and these equilibrium averages depends on instantaneous microscopic variables like positions and momenta, and such equilibrium averages could be pressure, it could be volume, it could be temperature, it could be potential energy, it can be kinetic energy, or it could be total energy, which are directly derived from the microscopic variables. But we also noted that there are certain properties which are dependent on the fluctuation in certain quantities. For instance, if you look at this derivation, that in a constant temperature ensemble known as canonical ensemble, if I measure the fluctuation in the total energy of the system, that is related to the heat capacity of the system. So if I can measure the fluctuation in energy, total energy, then I get an estimate for the heat capacity. Now the question is, what is the error involved in such a calculation of fluctuations? So to see this, we like to define the error estimate of fluctuation as very similar to what we have done for equilibrium average. So if you look at this particular formula, this formula is actually closely resembles the expression for the error estimate for the equilibrium averages. So you must be familiar with this particular expression, where we said that error in the variance in the mean is given as some correlation time tau c times sigma square A by tau run, where tau run is the length of the trajectory or length of the simulation data sets. So now what we can do is we can have analogous expression for the fluctuation also, and the fluctuations could be energy, could be any property that you want to study as a fluctuating variable. To see how this is derived, we can actually take this expression and then replace this mean with the fluctuation, because this expression is given for error in the mean, but we want to find error in the fluctuating quantities. So we replace this average A with fluctuation of A in this equation. So then we see that, and there is a factor of 2, additional factor of 2 that comes in, that's something added for convenience. And then you can see that this formula to this formula is simple replacing the mean value with the fluctuation. And after that, if you try to expand this sigma square delta S square, you can show that this simply becomes the delta S square ensemble average of that and then square of that. And then when you substitute this expression here, and you get this. So we take this as the definition for the estimation of fluctuations, error in the fluctuations. Now in this case, the correlation time tau c prime is defined again from a time correlation function, but now this time the time correlation function is within the fluctuation itself. Earlier we would have defined this. Okay, you can see this expression. So this is the expression we have used for correlation time from equilibrium averages. So you can see that this is something that we calculated as a correlation function. But here in calculating the correlation time for the fluctuations, instead of using the property A, we take the fluctuation in the property A in calculating the correlation time. So what it basically means is we are trying to get time correlation function of the fluctuating variable rather than the variable itself. And then you can actually show that if this correlation function here is an exponential decaying function, then we can equate the correlation time of the equilibrium average and the fluctuating average. So both can be taken as same. If this is not the case, then one will have to calculate the correlation function, time correlation function for the fluctuation, and from there integrate it and find the correlation time. In most of the cases, we can make this approximation where we find the correlation time for the property A itself and then use that as the correlation time of the fluctuation in A itself. So that approximation can be made. So we don't have to independently calculate correlation time for the fluctuations. We can take the correlation time for the equilibrium value itself, equilibrium average itself. So that once we know this TC, then we can use this formula directly and then get the fluctuation, error in the fluctuation, the variance in the fluctuation, and then get the tau C from this and then use to get that error in the fluctuations. So this should give us some estimate of what is the error involved in properties like heat capacity or thermal expansion coefficient, etc. Now there are also errors involved in structural quantities. For instance, we talked about this radial distribution function, and the radial distribution function is given as g of r, and it tells that if I tag a particular particle and then if I go radially outward at a given distance, what is the probability of finding a neighbor at that particular distance is given by g of r. And this g of r also has certain signature depending upon the phases of the matter. If it is a liquid, like you'll have multiple peaks, and then if it's a gas, it just has only one peak. And then in the case of a solid, it will have a designated peak corresponding to the lattice symmetry. Now in this case also, what we can do is we can calculate the error estimate, but instead of calculating error estimate for the entire g of r, typically we choose certain points, maybe the first peak, the second peak, and the minimum between these two first peaks. So generally people try to find the error bar about these places, these three places, and sometimes we can also get what is the error involved in the last point as well, r tending to a very large value. Now to see this, how error estimate on g of r can be made, then we look at the definition of g of r that we use to calculate g of r in simulations. So if you remember, there are two things we do. One is we average over the number of particles, and then we also average over the time. So here time step is given by this m, where m goes from 1 to, sorry, the index k goes from 1 to m. So this is basically time averaging. Okay. So what we have done here is we take pairs which are separated by a distance corresponding to the first peak, second peak, and the first minima. So in those places we do both number averaging and then time averaging. So instead of doing time averaging, what we can do is we can calculate this g of r max 1. So r max 1 would be this one, similarly r max 2 would be this one, and then r minimum would be this one. So we can calculate g of r at those specific positions as a function of time. So we don't do time average here for these cases, we just measure those g of r value as a function of time, then you get this, and then we have a set of data of g of r corresponding to one of these positions as a function of time. Then we can do the simple block average method that we have discussed, and then get an error estimate for these places as well as here. Okay, so this is one way in which error estimate can be made in g of r. But if you look at research publications, you generally don't see error estimate being reported for structural quantities like g of r here, because generally what they do here is they look for the smoothness of this curve. So if the g of r is not very smooth, they basically do longer simulations, average over many more time points, so that it gets smoothed out. Seldom you see actual error estimate in these positions. However, if you do a simulation and then you make a decision based on the signature of g of r to identify maybe phases, to identify number of neighbors, then you want to know how accurately this g of r is calculated. So it is advised that if you end up calculating g of r for a given situation, and if you depend on g of r to get the physics of the problem, you better calculate the mean value, error values corresponding to this first peak and second peak. And it can be very easily done by storing GFR value as a function of time without doing time averaging, because later on once you write this data you can do time average and also you can get the error estimate as well for specifically those set of points. Then there are also certain properties which depends on the time correlation function. For example, if you remember, this diffusivity of a particle is given by the integral of the velocity autocorrelation function. So the question now is that what is the error involved in the calculation of time correlation function itself. So here we assume that the property A again follows the Gaussian statistics, which we have already proved, and then one can show that the error in the autocorrelation function is again given by some 2 times some autocorrelation time. This is the autocorrelation time at t equal to 0, that is at the beginning, and then divided by the length of the simulation, where here this autocorrelation function is again defined based on the fluctuation in A, or the autocorrelation function in A. And then once we get the autocorrelation time and then use it here, and we can easily estimate what is the autocorrelation function at t equal to 0. Using this formula we can calculate what is the standard error, and as you can see the standard error is actually independent of time. So this is one way in which you can calculate error in the time correlation function also. So the point is, we have looked at error estimates in various quantities. The most commonly applied methods are demonstrated for equilibrium averages, and later on we defined the error estimate for the fluctuating fluctuations, then on the structural quantities, then on time correlation functions. So essentially all the measurements that we make in simulations should be reported along with some error estimate, and these error estimates are statistical so far, and then we have looked at various methods by which we can measure these errors. Now we will look at the other type of errors which are known as systematic errors. So in the beginning itself we said that errors are of 2 kinds. One is a systematic error, the other one is a statistical error. Systematic error is something that depends on how we conduct our simulations, what are the parameters that we specify, what are the algorithms that we use, in which way we actually conduct the simulations. Whereas statistical error is to do with the length of the simulation and what is the statistical variation of the quantities within. It all depends on the duration of the simulations. So now coming to systematic error, the systematic error basically what it does is it basically changes or displaces the computed average from the true average. So true average may be something, and then you might get a computed average which may be slightly different from the true average, and it may happen that statistical error may be small. Based on the method we already discussed, we might ensure the statistical error is very small, but the systematic error may be still large, and this will lead to a computed average which is precise, but it is an incorrect measurement or a wrong measurement because of the systematic error involvement. So it is very important for a simulator to take care of both systematic error as well as statistical error. And there are some systematic error which are very easy to detect, because when you do the simulations you will see some large numbers coming up and the simulation getting blown up because of some error in the code, or some properties, some model parameters are wrongly fixed. So such a systematic error can be easily identified by looking at how the simulation process proceeds. But there are many other systematic error which are not very easy to detect, and unless we are careful we may kind of just ignore them and focus only on the statistical error. So it's very important that we give due consideration not only to the statistical error but also to the systematic error. So now we will discuss a few points by which we can detect or try to understand where is this statistical error may come from and how do we eliminate it. So one of the simplest thing we can do is we can check whether a certain measurement that we make in the simulations do follow Gaussian distribution or not. We have already established that any property that we calculate in MD simulation under equilibrium should have a Gaussian distribution. So now what we can do is we can check whether such a distribution is established or not. So the way we do that is, we know that the systematic error, it not only changes the computed average, but also it changes or bias the distribution about the average. So we know the distribution has to be Gaussian. Now we can check whether the distribution is actually Gaussian or not. So to do that, we do what is called the chi-square test. And so what this basically means is, so this is actually shown in this particular graph. So here the distribution of temperature is given in a, let's say, in NV simulations. So in this NV simulation, temperature is a fluctuating quantity, And then if you look at how this temperature is distributed, you will see it's a Gaussian distributed, and the continuous curve that you see here is a theoretically calculated Gaussian curve based on the mean and variance in the simulation, whereas those points that you see here are the distribution calculated in the simulation itself, and you can see that the distribution is pretty much follows the theoretical expectations. So then if you do a chi-square test defined by this formula, you will see chi-square is close to 0. That means the two distributions are nearly matching. So what we do in this case is we divide m number of observed values of A, in this case temperature. Suppose if you make measurement of temperature, you know there is a range with which the temperature is changing. It might go from, let's say, some 200 degrees Celsius to 210 degrees Celsius. So that's a range. Once you have the range, then you basically make a histogram over a NB number of bins, so that this histogram can be made. So that those are the circles that we see here. For the entire period of entire number of data points m, we take NB number of bins, and then we look at the histogram, how this temperature is distributed, and then you see this kind of a Gaussian distribution. And then to do this chi-square, what we are going to do is, for each of this bin width or the bin size, we calculate what is the number of values of temperature in that particular bin, and then subtract that with respect to the theoretically calculated number of measurements in that particular bin, and then you normalize that. And then if they are exactly matching, that is, if the number that we measure in the simulation and the number that we calculate from theoretical estimates are exactly equal, you see the chi-square should go to 0. If that is not the case, you will see chi-square being something finite and non-zero. So that gives an indication that there seems to be some bias in the distribution obtained from MD simulation compared to what is theoretically expected, which is a Gaussian distribution. So for the theoretical estimate, we obtain the number of data points in a given bin k obtained from the Gaussian distribution. This error here, that is a standard deviation sigma, and the mean, these come from simulations. Okay, so we do MD simulation and then find what is the mean temperature and what is the standard deviation in the temperature. Using that, we try to fit a Gaussian curve, and then once we have the theoretical estimate, then we calculate how many number of data points should be theoretically expected for a given bin size, and that is what this NEK is, and that is compared with what is an actual number of measurements of temperature in a given bin for the same given bin, and that is what this chi-square is all about. So we look for this condition that chi-square is going to 0, so that the observed distribution agrees perfectly with the Gaussian. So this is one way in which you can check whether there is any systematic error or not. If there has been any systematic error, if that were to change the distribution of temperature from Gaussian to something else, then that is very easy to detect from these kind of tests. The other effect comes from the system size. What we generally do is we do simulations with a different number of system size. In this case, you can see that the temperature is measured for 108 particle system, 160 particle system, 256 particle system, 500, etc., etc. And then you can draw a fit, you can find a linear line fit, and then extend this to n tending to infinity. Okay, so when n tending to infinity, that will be the thermodynamic limit, and then you can report, and we can eliminate the system size dependence by this way. The same thing is given in the energy here, energy per particle. So here, if we are plotting as a function of 100 by n, so when n goes to infinity, that is the thermodynamic limit, so this will go to 0. Okay, so this would be the thermodynamic limit here, because this is where n goes to very large value. So you might have done simulation only up to certain this point, but then by fitting this straight line and then extending this to 1 by n tending to 0, we can find what is the thermodynamic limit. And the same thing is shown here also, where we find the compressibility factor as a function of 1 by n or 100 by n, and then we do measurements with the different particle sizes, each of these, and then you can see there is also error estimate from some of the methods we discussed before, and then we extend this line all the way up to 100 by n tending to 0. This will happen when n is very large. So this way we can eliminate the system size dependence on the simulated results. So when you report compressibility for this particular simulation, we should be giving this value. Similarly, for this simulation, these are the values we should be reporting, which doesn't depend on n anymore. Whereas anywhere in between, you can see there is a weak dependence of particle size on the measurement of energy. So generally, there are some guidelines given to verify, to check whether there is any systematic error in the simulations. For example, you could repeat the runs, the simulations using the same code but on different computers. So this is to make sure that the computer architecture is not giving any systematic bias or systematic error. Or you could actually repeat the runs using the same code but on different compilers, because sometimes compilers also have their inherent architecture and variability, and we want to ensure that that doesn't give any systematic error. Or we could actually run simulations using the same algorithm but different code written by, let's say, different programmers, just to make sure that the value should not be dependent on the code itself. And then repeat the runs using different algorithms. For instance, if you do MD simulations, we have discussed various equations of motions algorithms, Verlet, velocity Verlet, leapfrog. So you could do the same simulations using different integrator and check whether any systematic error from those simulations. Sometimes we can even run simulations using different simulation methods itself. That is, you can do MD simulation and you can also probably do a MC simulation, given that MC simulation also gives you the same results, and then check. In this table, hard sphere is simulated for different packing fraction using both MD. So in this table, the compressibility factor is measured for hard sphere system at a different packing fraction or different density using both MD simulation as well as MC simulations. And you can see that these values are very closely matching, even though the simulation techniques are very different. One uses equation of motion, other one uses a random sampling or umbrella sampling, and the way in which we do the simulations are quite different, but then you can see the estimates are quite good. And then you can also see not only the mean is reported, but also the error estimate is also measured for each of these cases, and you can see close equivalence of the values between those two. There is a small variability in but within the error estimate. So this is what this last point means, using different simulation methods. But these are some of the guidelines. One need not do all these checks, but I think one or two checks is important. But we have to keep in mind all the time that these are the sources of systematic error that might come in. And then whenever you see something unusual in your MC simulation, or whenever you plot the data and you see something unusual, you can actually go back and then do these kind of tests to verify whether those abnormalities are coming because of systematic error, or is it coming because of a true physics of the system itself. So with this, so we could actually summarize that we looked at this very simple block average method for getting statistical error estimate for a equilibrium property, and we also showed how to define and calculate errors in the fluctuations, structural quantities such as radial distribution functions and the time correlation functions. And we also looked at few points by which the systematic errors can be checked, where you can look at whether a measured property obeys a Gaussian distribution or not, and we can also check whether the system size is affecting the results or not. And then we also looked at some general guidelines to detect the systematic error, which basically involves running the simulations in different compilers, different computers, or using different algorithms or different simulation techniques itself, by which we can see whether any systematic error has come in picture or not. So if you look at published results on MD simulations, internally these verifications are usually done. So, and if you do MD simulations in the future, so you have to keep in mind of all these important points with regard to error estimates, whether it is a statistical error or a systematic error. And we should also make sure that we have, to the best of our knowledge, that we have eliminated those source of error. And like I was saying before, all your measurements should be given in this kind of a form, where the mean is given along with an error estimate, so that we know what is the variability in these measurements. And these measurements, as I said, it depends on your system size, and then your statistical analysis all should be done to ensure that a proper error estimate is done. Without giving this error estimate, if you give only the mean, then it gives a very uncertain feeling that how much variability in this average could mean. So it's very important for us to measure error and then report them like this.